we'll study the further topic of the steam turbine, which is the blade or diagram efficiency. Okay. So to choose a pen, let's do this. Okay, fine. So it is a term used to indicate effectiveness of blade in transferring incoming energy into useful work. It's called the blade or diagram efficiency. So how can we define this? It is the ratio of work done by the blade to the energy to the inlet of the blade. So this is the blade of the blade we can say. So what we have calculated with the help of the velocity diagram, that we are getting this power, this much of power we are getting from the blades. Fine. Hmm, fine. This is fine. Fine. Hmm. This much of power we are getting, and what when we have drawn the blade diagram, then the velocity is coming from this diagram, that is v1. So the whole kinetic energy which is getting this m dot v1 square by 2. So blade diagram is efficiency is the uh, it is just the capacity of how much useful work we are getting from the input of the energy. So input energy is which the steam contained in it. It is the input of the energy. And how much energy we can consume from that steam is defined by the diagram or blade efficiency. So after manipulating it, calculating it, we can get 2u Vw1 plus Vw2 upon V1 square. So uh, better to remember this formula. Okay. Now, how can we define the maximum blade efficiency? For maximum blade efficiency, we can differentiate this blade efficiency. Okay. So here is a trick to find out the maximum blade efficiency. Uh, whatever is whatever velocity is given, first convert in u, because with respect to the blade velocity, we want to find out the what should be the efficiency and what should be the maximum power, because blade velocity is in our control. How much blade velocity we can do, because the steam velocity, outward velocity, inward velocity, we are not able to control it, but blade velocity we can control so that we can get the maximum efficiency. So for that, first of all, we will convert all the velocities in terms of u. So first let us see Vw1 plus Vw2. We can convert. For that we have to see that blade velocity diagram. Mm, okay, let us. Hmm. From this blade velocity diagram, we will clearly understand what is going on. So Vw1 we can write from here. We can say that hmm, Vw1 can be written as Vr1 cos theta plus Vr2 cos phi plus Vr2 cos phi. Okay, we will take common Vr1 cos theta is equal to 1 plus Vr2 upon Vr1 cos phi 1 cos theta. If we will define Vr2 upon Vr1 as k, because this is frictional coefficient. Okay, this is frictional coefficient, and this is cos phi 1 cos theta. It is also constant. Both are constants because these are the blade angles. So Vr1 cos theta is equal to 1 plus kx. Now Vr1 cos theta, we can say that it is Vw1 minus u, and Vw1 is equal to V1 cos alpha. So VR1 cos theta is equal to V1 cos alpha. Okay. So VW1 plus VW2 can be written as V1 cos alpha minus U into 1 plus kx. So we'll now we can see. So we will okay, something wrong is happening here. We'll listen. Okay, now we came here. Okay, now uh, uh, put u inside, then we'll get 2 into v1 u cos alpha minus v square 1 plus kx upon v1 square. And now we will define a term speed ratio u upon v. Okay, so we'll convert, it will be constant, rho is equal to constant, whatever will be u and v1. Okay, because we have already, it is our constraints here. Okay, so blade efficiency will be 2 into rho cos alpha minus rho square 1 minus kx. Now we will differentiate with respect to the rho because we have here two variables. So we are trying to convert in single variable. Okay, whatever will be the we are getting, that will be the our constant for the maximum efficiency. Okay, so when we have differentiated, we are getting the rho is equal to cos alpha by 2. Okay, it means that it is very basic, fundamental and very important relation. Rho is equal to cos alpha by 2 for maximum efficiency, maximum blade efficiency. Rho is equal to cos alpha by 2 is equal to u upon v1. Or we can say that cos alpha is equal to 2u upon v1. And the maximum blade efficiency, we will get that cos square alpha by 2 into 1 plus kx. If there is zero friction, then maximum efficiency will be cos square alpha for frictionless blade. Okay, okay, so usually the blade angle is 15 to 20 degree or 18 degree we use. And because alpha is not equal to 0, alpha is not equal to 0, so v of 1 is equal to 0. What does it mean? Let us try to understand it. Alpha is not equal to 0, here here alpha is not equal to 0 because v of 1 is equal to 0. Okay, understood? So the main formulas we are getting, that maximum blade efficiency equal to cos square alpha by 2 1 plus kx at rho is equal to cos alpha by 2. Okay, maximum blade efficiency is equal to cos square alpha. Fine. So what is our next topic? Can we gross efficiency? We can define that nozzle or uh, nozzle and moving blade combine together to make a stage of impulse turbine. Gross stage efficiency is the ratio of actual work done by the blade to the isentropic enthalpy drop possible in a nozzle. Whatever isentropic enthalpy drop is possible in a nozzle, how much actual work we can get. Okay, so that is defined as the whatever work we are getting divided by HS drop. How much enthalpy drop we are getting and how much we have collected the work from that. So gross efficiency we can define by this. So we are multiplying and dividing by HA. So gross stage efficiency we will get this HA will be V1 square by 2 actual enthalpy drop, and that is isentropic enthalpy drop. Okay, so actual enthalpy drop of an isentropic enthalpy drop is equal is called as nozzle efficiency. So gross stage efficiency, we will get that blade efficiency into nozzle efficiency. Okay. Pressure compounding through we are getting more efficiency, which is getting practically difficult because nozzle moving blade, we have to manage. Then we'll cover the carryover coefficient. What is carryover coefficient? It takes into account the amount of kinetic energy lost in between the stages. Whatever the kinetic energy is lost between the stages, that is called carryover coefficient. It is a fraction of kinetic energy which will be available by utilizing in the next stage compound compared to the preceding stage. Fraction of kinetic energy which is available for utilizing for the next stage. Two row practice. If you are talking about two row practice, then let's say this is our first stage, this is our second stage. Velocity is coming here, velocity is getting here. So here, whatever kinetic energy is getting here, whatever left we are getting here, and this is here. So let's define the phi term, carryover coefficient phi here will be final minus initial. Here the final minus initial v1 double dash by square by 2. Okay, so the whole power we will get that m dot equal to vw1 plus vw2 plus vw1 double dash plus vw2 double dash into u. So for two row curtis, blade speed remain the same for both the rows of moving blade. For two row curtis, blade speed remain the same for both the rows of moving blade. Yes, and fixed blade outlet angle become nozzle angle for the second row of moving blade. Yes, fine, that's clear. So this is called the carryover coefficient. So try to remember it. It is the how much kinetic energy is available for the next stage of the steam turbine. That is called. So in the next class we'll cover the reaction turbine. Thank you so much.